Welcome. This video is designed, if you're having a little bit of trouble with this weekend's homework on volumes of revolution. I'm hoping that you tried them a little bit before you watch this video, because I'm going to work through 1ABC, which is what was assigned, and give away kind of the solutions of how we would set these up using either disks or washers. So for all three problems, the boundaries are the line y equals 3 minus x equals 0, and y equals 0. Okay, so for the first problem, part A, we are revolving that bounded region by the x-axis. So I'm going to draw a picture of what's going on, and since I'm using the x-axis, I'm going to make my first and second quadrants much more apparent. I'm going to use some different colors for each of my curves. So we'll use red for 3 minus x. I'm just going to ballpark. I'm not going to count exact dots, but because at this point in the game I know the general shape of this. We know it's going to start at 3 on the y-axis, and it's going to come down and hit the x-axis at 3. Then we can do some of our other lines, so we know that x equals 0 is going to be right here on the x-axis. We know that y equals 0 will be the x-axis. And this right here is now our bounded region that we're going to rotate. And we're going to rotate it about the x-axis, like so. So now we can draw some mirror images. So down here at -3, we go up to 3. And then, of course, the axes, again, are the other bounded points. So now this entire thing would be a two-dimensional look at what the three-dimensional solid would be. Okay, so as we rotate it, and we make a cut into this solid, we notice that the cut is going to be a solid disk in and of itself. Okay, and it doesn't matter where you draw the disk, it's still going to be a solid disk. So essentially the setup is just we're taking an infinite number of these really paper-thin circles, finding their areas and adding them up from the y-axis out to x equals 3, which gives you an idea of your limits of integration as well. So at this point, all I really need to figure out is what is the radius of one of these circles in general. Okay, now, let me help you out a little bit, because I think when we get to the washers in the next example, it's going to make life a lot easier. And I tried to allude to this on Friday, but with the shortened class and it being brand new, I don't know if it was quite understood. The radius, every expression you write for a radius is basically like we did in the last section on an area between two curves. Top minus bottom if we're doing a dx cut like this. Right minus left if we're doing a dy cut, which we'll get into in class tomorrow. Okay, so if you look, what are the two curves we're talking about? We're talking about the line y equals 3 minus x, the red line, and the x-axis, also known as y equals 0. So what is the radius of the disk? 3 minus x. Technically 3 minus x minus 0, but we can just drop the 0. So that's your radius. So that means one disk has area pi r, which is 3 minus x squared. So if we want to get the volume of the whole solid, we're going to take that disk and we're just going to accumulate them up from 0 to 3. So we get 0, 3, area of one disk, pi, 3 minus x quantity squared, and then the thickness of the disk, we call that dx. Okay, we can pull the pi out, so now it's pi integral from 0 to 3 of the quantity 3 minus x squared dx. If you've got that set up, then you can go to your calculator and you can get the right volume. You could also FOIL this out if you don't have your calculator in front of you to do all this and take the antiderivative. Either way, the final answer should be a volume of 9 pi. Okay, so that's how we would set up part A. Next, we're going to do the same picture, but we're going to rotate it in a couple different lines, and we're going to get some washers out of it. Now, if we look at question part B, same three equations, y equals 3 minus x equals 0, and y equals 0. But now, we're going to rotate it along the line y equals 3. Okay? So again, let's draw our x and y axes. Now, I know, based on what the shape from A was of the bounded region, I know it's a right triangle that's sitting on the x-axis. If I'm rotating it up at 3, I need much more space above the region in order to get the proper rotation. Okay, so I would say, especially if you have a blank piece of graph paper and you have to draw these, think about, visualize where it's going to go so you can get your axes accordingly to fit. Alright, so let's put in, first thing I want to do is, I'm actually going to put in my line of rotation very, very first. So here we go. We'll make this be the line y equals 3. So that's going to be my mirror image. Alright, and let's try to use a similar color scheme from before. So we're going to start at 3 here, and we're going to go down to 3 on the x-axis. And then we've got the line x equals 0, and the line y equals 0. Okay, so now we are taking this bounded region that I'm highlighting here, and we are going to rotate it about the line y equals 3, right here. Okay, so it's going to come off the screen and back onto the screen, and when it comes back onto the screen and hits the graph paper that I have, you're going to see basically this kind of mirror image as I'm drawing here. So there's 3 minus x, there's your x equals 0, and here's your y equals 0. Okay? Now, because there's this white space right here, when we take our cut and we slice straight through our screen and straight through the graph paper, we end up getting an outer circle as well as an inner circle with nothingness in between. This is our so-called washer. Okay, right here is empty space. So how are we going to figure out the area of this washer? Like we said in class on Friday, we are going to take the area of the bigger purplish circle, and we're going to subtract from it the area of the little red hole that we have. So we need to get 2 radii here. The big radius, which your notes call it capital R, and the small radius, which we call lowercase r. Well, now that big radius, again, we can use our mentality of the area between 2 curves. The top curve is the line y equals 3. The bottom curve is the line y equals 0. So what would that radius be, whether I draw it here, here, or here? 3 minus 0, which is 3. So big R is 3. Now we need to do the same thing with the little radius. So again, where do we start? At the center, y equals 3. Where do we stop? The line y equals 3 minus x. I don't care if you draw the little circle there, or you draw the little circle there. It's still going to be 3 minus x. So little r in general must be 3 minus the quantity 3 minus x, which, if you can simplify it, why not? Look, 3 minus 3 is 0, and then minus negative x becomes positive x. So little r is just x. So now when we go to set up our volume, we're going to do pi times the integral from 0 to 3 again, because that's still our upper and lower limits for vertical slicing on the x-axis. Now we do the area of the big circle, which is going to be 9, because the radius is always the constant, 3, minus the square of the radius of the smaller circle, which we simplified to be x, so 9 minus x squared dx. And I should put the dx, or the parentheses around the whole 9 minus x squared to let the reader know I'm integrating the whole thing. And again, you can go to your calculator for this. You would get 18 pi as the volume of that solid. Alright, so now there's one more we have to cover, and we have to look at what I consider the more challenging of the dx problems, and that is where you're not rotating right at a corner of your bounded region. You're rotating a little bit of a ways, okay? And that's going to be part C. So now the last part of the assignment, same three lines, y equals 3 minus x equals 0, y equals 0. But now we're going to rotate it about the line y equals 6. Okay, so I'm going to go draw my graph of this, and I am going to basically stick to the first quadrant, so I have lots of room to show you what's going to happen. We'll start this time by doing the line of rotation. So we'll do the line y equals 6, and maybe we'll make this 6 on the y-axis. So this will be my rotational line. Okay, so I'll try to do the best I can to draw this to scale. So that's got to mean the line y equals 3 minus x will start about here, halfway between our rotational line and the origin, and then we'll go down to here. We'll call that x equals 3. And then again, we use our axes as our other boundaries. So there's x equals 0, and there's y equals 0. And yet again, kind of like a broken record, we are highlighting the shaded region, that's the bounded region that we will rotate around the line y equals 6. So when we rotate it around the line y equals 6, again, we need to get our mirror image. So what will happen is the red line will actually now start up here at y equals 9 and go like that. The line x equals 0 will just follow suit 3 units down the, or up the x-axis, or the y-axis, excuse me. And then the line y equals 0 now becomes over here at, I guess this would be y equals 12. That, not as big of a deal knowing that kind of stuff. Really the key is understanding, what's the top, what's the bottom function when we draw our circles. So here we go. We look at a cross-section of this rotated figure. And you can see that we're going to have a hole again in the middle because in between the line y equals 3 minus x and its mirror, there's nothingness. We're rotating with so much space in between the red line and its mirror image because now our line of rotation is actually above the bounded region. Okay, so that's going to make a big difference when it comes to setting this up. So let's start with figuring out what our radii will be. So we'll start with the radius of the larger circle. It's centered at the line of rotation, y equals 6. And we go down to the x-axis, x equals 0. So I think this radius, and again I can draw a couple other radii, regardless of where I draw it in that bounded region, I think this big radius is always going to be 6. Okay? Now let's try to do the same thing with the red, the smaller circle, the hole. Again, we're starting at 6, and we're going down to the red line. Doesn't matter where I draw, we're still starting at 6 and going down to the red line. So that means, if we think about it in terms of an area between two curves, the little radius will be 6 minus 3 minus x, which now when we distribute our negative, we get 3 plus x. So that is going to be, in terms of x, the length of every one of these red radii that I have drawn. Okay? So, one washer then would have area 36, because that's, well, pi rather, times 36, because that's the area of, or the radius of the big circle squared, minus 3 plus x quantity squared, because that's the radius of the red. So this expression tells me what one of these washers' areas would look like. If we sum them all up from 0 to 3, we now get the volume of the solid. So we would get that the volume would equal pi times the integral from 0 to 3 of 36 minus the quantity of 3 plus x squared dx. And that's how this one would get set up. And then from there, you can put that in your calculator and integrate, and you get 45 pi. Okay? I hope these videos and I hope this demonstration of these three problems helps. I'm hoping that we won't have to go over too much of this tomorrow in class. We can move on and look at some other examples and start looking at some dy examples where our slices are now going to be parallel to the y-axis. Or excuse me, they're going to be parallel to the x-axis, so they're going to be horizontal slices, which means we'll have to use dy. If you have any other questions, please feel free to ask me. I know this is tricky, but with much more practice setting them up, you will get it without a problem. All right, I'll see you in class.